Hi everyone, and welcome to this new video on IT network addressing. My name is Gaspar Mbole, your IT network engineer with Smart Technology Consulting. This video comes after the first one that we released, where we explained what addressing is, why we need addressing in network, and where we use these addresses and the devices that are used to manage and to handle a device's addresses. And if you recall in that previous video that I invite you to go and watch, you will see that the addressing is the way of identifying devices in a network so that these devices can communicate smoothly. And we ended that video by showing that we can manage the addresses right at layer 2 where physical signal is received so that devices can be acknowledged there clearly. But we had a problem that these addresses are assigned by the manufacturers, so we don't really have total control over these addresses as network engineers. The reason why we want to find another way of addressing devices so that we can have control over this. And for that purpose, we're going to have another layer of addressing, which is layer 3. And we call the addresses that are managed at layer 3 IP addresses. So we're going to talk about that, and then we'll spend a little bit of time in the math of those numbers, because it can be a little challenging to understand how we move from 1 and zeros to different numbers, right? Because computers, they understand 1 and 0. But we're going to manipulate other kind of numbers to make it easier to understand. So we're going to spend some time explaining these math that go in the conversion and how to manage this. So let us talk about layer 3 addresses. You recall that we explained in the previous video that layer 2 or MAC addresses are existential addresses, right? Because these are addresses that are assigned by the manufacturer. And the problem is that we can't really have any control or any decision on on this addressing. We get the computers with the network interface card, and they come with these physical addresses already. So how are we going to decide what role a device should have in our environment? How to identify it? That's going to be a challenge. That's why we're going to have another layer of addressing on top of that one, which is going to permit us to assign a job to a device, and that's what we call it an operational identification, because that will permit us to decide that this device is going to be a server, or let's say a domain server. This other one is going to be the DNS server. The third one is going to be a file server. When this fourth device will just become a client. So this flexibility is what we're going to have by assigning logical addresses on top of physical addresses, right? Because the physical address is going to be like the name of a person, and the logical address is going to be like the role of that person, right? Imagine a staff member who is a CIO for now, and is going to get promoted as the CEO. It's the same person. MAC address that is going to have different role, IP address. I hope we understand the difference between the two. And of course, we're going to need a different kind of devices to handle this kind of addressing. This is what we call the layer 3 devices, and among which we have routers that are basically built to understand these kind of addresses, right? And we have two flavors of IP addresses. Initially, we had the version 4 of these addresses that we call the IP version 4. And those addresses were coded on 32 bits, grouped in 8. So that makes 8 bits for an octet. That's why we have an IP address that is made of 4 octets separated by a dot. So it's going to be octet 1 dot octet 2 dot octet 3 dot octet 4. Each octet has 8 bits, and those 4 octets in a total we have 32 bits. But with the number of devices connected, on networks, we're kind of running short of addresses. That's why we have the second flavor, which is the new version of IP addresses, that is already been in use now, the IP version 6. That one is coded on 128 bits. It's 128 bits long, which is 4 times the size of the IPv4. And for that one, we use the hexadecimals. You want to see that for the IPv4, we use the decimal numbers, and the value of each octet is going to go from 0 to 255. But for the IPv6, we use hexadecimals. We have 32 of them that make, a whole IP address. And whatever version we use, an IP address has 2 components. The same way we had 2 components with the MAC address, right? You remember, on a MAC address we have 12 hexadecimals. The 6 first hexadecimals will uniquely identify the manufacturer. The 6 last will identify the device that manufacturer has made. And when we combine the 2, we get a unique MAC address. The IP address is going to follow the same philosophy, where we have a part of that address identifying the network in which the device is member of, and the other part identifying the device within that network. And the separation here is going to be made with the network mask, which is going to identify which of those bits are to be considered for the network, and which bits are going to be considered for the device. So that when we mix the two, we get the whole IP address of the device, and we can then identify it in a precise network. We will do a couple of examples in the future videos so that we see how we manipulate this. But let us take some examples so that we see how these addresses look like. An IP address version 4 is going to be like 192.67.53.124. You can see we have 4 numbers, which are the 4 octets of the IP address version 4. And for the version 6, we have an example there, and you can pause the video to read that long address, right? So those are the 2 examples. And in these, whether version 4 or version 6, a part of that address is going to be the identification of the network where we find that device, and the other part, the identification of the device within that network. Now let us spend some time, a little bit of time on this screen here so that we can see why we need an IP address. The same way we use those addresses, we use the addresses, the MAC addresses on the Ethernet frame, in the same way we're going to use them in the IP packet. You will see that here we need to clearly identify the source and the destination so that the data that we have in the big gray box there will have, will flow easily between the devices that are supposed to be in communication. So we need in each packet to identify who is sending the data and to who the data is sent. right? This is going to permit to avoid, information that is going in other direction. Now, let us look at this fun part of our video. One of the fun things that I like to do in this networking is to understand, the magic between the binary and the decimal. I know it can be kind of challenging to understand how we move from binary to decimal, but we tried to make things a little easier so that you can follow. And of course, you can pause anytime to have a better understanding. So let us first of all get from some concepts clear. An octet is a set of 8 bits, right? You remember the IPv4, four octets. Each octet is a set of 8 bits. And a bit or binary digit has a value of 0 or 1. Now, in this chain of 8 bits, each bit has a position. And the position of a bit in a chain determines the power of 2 it represents in reverse count. You can read that sentence slowly, and I'm sure you're going to understand that the position of a bit in a chain, in a series, determines the power of 2 it represents in the reverse count, right? And the value of that bit will be obtained by this formula. The decimal value of a bit equals the binary value of that bit times 2 at the power of 8, 8 being the size of an octet, minus the bit position in the octet, right? It's very straightforward. If we want to determine the digital value of a bit, we need to take the binary value of that bit and we multiply it by 2 at the power of the size of an octet, which is 8 bits, minus the bit position, the position of that bit in the octet. Let us take an example to make this a little easier to understand. Let us consider this series, this octet. We're going to ignore the other XXXX and we consider the 1 there. So we want to determine the decimal value of the 1 that appears in this chain. XXXX, 1, XXX. First question, what's the position of that 1 in the chain? Of course, you are right, it's the 5th position because we count from left to right. So it is the 5th position. So what we're going to determine, how we're going to determine the digital value of that bit? It's going to be the binary value of that bit, which is 1. Remember, it should be 1 or 0, but in this case it is 1, times 2 at the power of 8, 8 being the size of an octet, minus the position of that bit in the octet. What's the position of the bit in the octet? 5. So it's going to be 1 times 2 at the power of 3. 3 is 8 minus 5, right? And when we do the math, the value is 8. And we have to determine the decimal value of each bit in the octet so that we can sum all these values and get the decimal value of the entire octet. So that decimal value is going to be the sum of all the decimal value of the bits that make that octet. It's very simple. Let us take an example to make this easier again, a real example. Imagine we have this octet 10011011, and we try to give them different colors so that you understand which bit we are using at what level. And we have the order of the position below. Let us recall our formula here to determine the decimal value of each bit. Remember, it is the binary value of the bit times 2 at the power of 8 minus the bit position in the octet. Let us start with the first bit, which is 1. The blue bit. It's 1. Its digital value will be 1. times 2 at the power of 8, which is the size of the octet, minus its position, which is 1. That gives 1 times 2 at the power of 7. And when we do the math, we get 128. Next bit. Bit at the position 2, it's 0. 0 times 2 at the power of 8 minus 2 equals 0. Anyways, anything times 0 is 0, or 0 times anything is 0. We don't need to break our head too much there, right? Third bit, the green bit, it's 0. And we do the same formula, we get 0. Fourth bit, the red bit, the value is 1. The binary value is 1. So it's going to be 1 times 2 at the power of 8 minus 4. We do the math, we get 16. The fifth bit, when we do the math, we get 8. The sixth bit, which is 0, decimal value is going to be 0. The seventh bit, the black one, is going to be, the value is going to be 2. And the last bit, the value is going to be 1. So this is how we get the digital value of each bit in the octet. Now, and you have to recall that any number at the power of 0 is 1. That's why the 8 bit is 1 there, because we have 1 times 2 at the power of 8 minus 8. 8 minus 8 is 0. 2 at the power of 0 is 1. 1 times 1 is 1, right? Very easy to understand. So now we have all the digital values of the bits that make an octet there. The digital value of the octet is then going to be the sum of all these digital values that we have in this formula. And when we apply it, we get 128 plus 0 plus 0 plus 16 plus 8 plus 0 plus 2 plus 1. And this sum gives 155. That's how we get the value of an octet in an IP address version 4. And of course, if all the bits are 1, you can do the math, and you will find that the digital value of that octet will be 255. You can do a couple of exercises, give yourself some octets, and try to apply this formula. You can pause, and I know it's going to be easier for you. Now, we have to understand that we can also do the reverse. Decimal to binary. That is, we get a decimal. How can we go from a decimal number to an octet, a chain of bits? Let us see. The method is going to be a little different. Here, we're going to use a set of division. First of all, we have to understand that an octet has a value that is between 0 and 255. So don't use 263 and to try to create an octet with it. It's not going to work. There are going to be more bits than we should need. Now, when we get a number, we're going to do a set of division by 2 and consider the remainders. That is how we're going to build the chain of bits. Let us take a little example here. Let us assume we want to do the conversion of 209 to see what is the bit chain, the octet in bits that represent 209. We're going to do a set of divisions by 2, and then we take the remainders. So we go 209 divided by 2, we take the integer, that is 104, and then the remainder is 1. We take the 104, divide it again by 2, it gives 52, remainder 0. 52 divided by 2, we get 26, the remainder is 0. And then we continue this operation, right? And you can see how the remainders, we get them. And when we have the result of a division as 0, we stop because we can't go further. As the step 8 there, you see we have 1 divided by 2, result is 0, and the remainder is 1. Then we stop there. Then we will take the remainders from the first one to the last, and that's how we're going to have our binary value of the octet, right? You can ask a question, what if we don't have 8 bits? Very interesting question. That's smart. Let us take an example for that. Let us consider 53. And we do the same strategy. 53 divided by 2 gets 26, remainder 1. We divide 26 by 2, we get 13, remainder 0. 13 divided by 2, we get 6, remainder 1. 6 divided by 2, we get 3, remainder 0. And then we reach the 6th level and we stop. The problem here, we have only 6 bits. 101011. An octet is 8-bit long. So we need to complete it. What is going to happen is that we'll add 2 zeros on top of them so that we make 8 bits. Why do we add this? You see the octet value is 53. If you recall, the first bit, what is the decimal value of the first bit in an octet if it is 1? Exactly, it is 128, which is bigger than 53. So that's not going to be in our digital value. That's why we give it 0. The second bit, what is going to be the decimal value of that bit? Exactly, 64, which is still greater than 53. So you can see, since to get the decimal value of an octet, we have to sum all the decimal values of the bits. We cannot get 53 by summing something to 128 or to 64. That's why those are going to be 0. I hope this permits to understand the math that we have behind these numbers, from the bits to the binary digits to the decimal and vice versa. You can multiply examples and try to get familiar with this concept, with this math, and know that it can be tedious. But with a little bit of exercises, you're certainly going to get there. And this is going to wrap up our presentation of today. Please, if you have a comment, share it below. And do not forget to subscribe if you're new to this chain. And if you have a question, let us know, and we'll be very happy to share this with you, because our goal is to be smart with you. Until then, see you at part 3, where we're going to study new stuff concerning addresses. Bye, and see you soon.